We're almost done now with chapter 18. I wanted to go through another quick example just to illustrate something else for you. So with this new example, we're thinking about lottery tickets. So many states sell instant lottery tickets in which you scratch off certain areas to see if you have won a prize. You've obtained a random sample of 1,000 people who have purchased such tickets, and you're examining the proportion of these people who have won prizes. So we're giving you this sample size here because we want you to be thinking about what a sampling distribution would look like if we could look at lots and lots of samples of size 1,000 from this particular population. Again, each time we take a sample, we think about the sample proportion. So let's say that you know over time, if you could look at lots and lots of samples, that the sampling distribution of the proportion of winners would be approximately normal in shape. It's going to have a mean or a center of 0.2. So what this is essentially telling us is that in the population, 20% of people win prizes. The population proportion of winners is 0.2. So that's where our sampling distribution will be centered. It's going to have a standard deviation of 0.04. So knowing these pieces of information, this gives us a lot of really useful stuff that we can now use to answer some questions. Again, you don't have to do this if you don't want to, but I think it can help to sketch the sampling distribution, to really be thinking about where are you looking on this distribution. It can help you visualize how to answer certain questions. As you'll see in the next few slides, by drawing this, you have a great resource you can go back to and answer lots of really great questions. So I know it's normal. It's centered at 0.2. Here's the middle. Standard deviation of 0.04. So I went out 3 standard deviations on either side. So look really carefully at that curve. That's if we could take lots and lots of possible samples of size 1,000 and each time look at the statistics or the sample proportions, this is what that collection would look like. Here it is again. Let's use this to answer some questions. So what kinds of questions might you see? What percentage of samples chosen at random will have a proportion of winners greater than 0.28? So here's where drawing the distribution can help you a lot, because hopefully you're noticing you go out 2 standard deviations above the mean. Here's 0.28. I want to know what this little percentage is. If 0.28 falls exactly 2 standard deviations above the mean, think about the empirical rule. How can that help you answer a question like this? Remember, the empirical rule tells us that if we go out 2 standard deviations from the mean, we have 95% of our data. That means we'd have 5% left over. Half would be down here. The other half would be up here. So just from drawing this distribution and knowing the empirical rule, I can really quickly answer that question. The answer would be 2.5%. Now, of course, if you didn't remember the empirical rule, what could you do instead? Well, you could convert 0.28 to a z-score and use table B and arrive at a similar answer. It's not going to be exactly 2.5% if you use table B, because remember, the empirical rule is an approximation, but it'll be something close to that. But think about the fact that, converting to Z and then going to table B, and then once you're in table B, you're going to have to remember to subtract what you see in that table from 100 to get this little area up here. That's a lot of steps to go through and extra time to work through the problem that you don't need to take. So if you have a good understanding of the empirical rule, that can always save you some time in terms of solving these problems. Similarly, let's think about this next problem. What percentage of samples will have a proportion of winners less than 0.16? 0.16 falls 1 standard deviation below the mean. The empirical rule tells us that if we go out 1 standard deviation, we have 68% of our data. That means we'd have 32% left over. Since 100 minus 68 equals 32, half of that 32% will be here. So this will be 16%. The other half will be here, 16%. So the answer here is 16%. Again, if you weren't thinking about the empirical rule or you forgot about that, you could still answer this by converting 0.16 to a z-score and then going to table B. So again, if you did that, it would be z equals 0.16 minus 0.20 all over 0.04. So you can always fall back on converting to z. And if you really like doing that and are comfortable doing that, I want you to do that. So I want you to do what you feel is most comfortable and what's helping you most work through these problems. Finally, what percentage of samples would you expect to have a proportion of winners less than 0.14 or greater than 0.3? So again, less than 0.14 is over here, 0.14, less than, greater than 0.3 is going to be up here somewhere, 0.30, so this little chunk. So these are cases where 0.14 and 0.30, unfortunately, they don't fall exactly 1, 2, or 3 standard deviations from the mean. So in that case, you would have to convert to z. You would, again, have to go to table B. So quickly, I'm going to just show you what this would look like. I want you to practice it on your own and make sure your answers match mine. So here it would be z equals 0.14 minus 0.2 over 0.04. That's going to give you negative 1.5. And then if you go to table B, you'll see from table B that negative 1.5 corresponds to a percentage of 6.60%. For greater than 0.3, we again need to convert this to z. That's going to give us 2.5. If you go to table B and look up 2.5 as a z, you end up getting, oh, let me double check here. Forgot to write this down. So you go to table B and you look up 2.5, you're going to get a percentage of 99.38. Obviously, this little chunk here is not 99.38%, so we have to subtract that number, 99.38, from 100. So the final answer here ends up being 0.62%. So again, another reason I think it's great to draw these curves and to shade in or highlight where you're looking is that it can help you gauge your answer. So you might go to table B and think, okay, the answer has to be 99.38, but when you're looking back here and seeing this really small percentage or the small area, hopefully that'll be a wake-up call as to whether 99.38 is actually the best answer for that question. Finally, we're going to go back to Reese's Pieces. So I want to see what you learned here from this presentation. I want you to try to answer this question without doing any calculations. And I guess I should say there's one little calculation, and that's just to put the sampling distribution together. But we already have the sampling distribution. So remember back early in the presentation, we were thinking about taking samples of size 50. And we talked about what would happen if we repeatedly did this. We'd get this sampling distribution. You might remember I told you it would be centered at 0.5 with a standard deviation of 0.071. So this is the same distribution we looked at earlier when we answered some Reese's Pieces questions. Now I want to know what's more likely, meaning which of these two things has the highest probability of occurring and why. Is it more likely that you would get a sample of 50 Reese's Pieces where 20% or fewer of the candies are orange? Or is it more likely you'd get a random sample of 50 candies where 60% or more are orange? So there's a couple ways you can think about this. And this is hopefully will kind of lead into some of what we'll talk about in the next set of videos for chapter 21. But again, if you have that distribution drawn, simply mark off where we're looking here, 20% or fewer. So 20% or fewer is going to be out here somewhere. Pretty small probability of observing that. If in the population 50% are orange, it would be unlikely that we'd see 20% or fewer orange in a sample of size 50. What about 60% or more? Well, 60 is over here. So obviously this area is larger than this area. So it's more likely, it has a higher probability that we'd see 60% or more. Another thing to kind of be thinking about is that if we imagine that we're repeatedly sampling from a population that has a particular parameter, in this case 50%, we would expect that if we're randomly sampling and we're collecting all those sample statistics, that the statistics are going to cluster around that parameter. You're going to have a lot of the statistics are going to be close to that true parameter, and then they start to trail away from the parameter. So 60% is obviously larger than 20%. 60%, or let me backtrack here. 60% is obviously closer to 50% than 20%. 60% is closer to that true parameter than 20%. And so based on what we know about sampling distributions and how they behave, if what tends to be around the parameter are values close to the parameter, and if 60% is closer than 50%, we'd expect the probability of seeing something like 60% or more would be larger than the probability of seeing something that's so far away, like 20% or less. 20% or less is much further away from 50%. I'm hoping that's making some sense. As I was hearing it come out of my mouth, I'm not sure if it did, but I want you to think about this. I want you to just to reflect on this a bit. And again, this particular set of slides, you might need to go through one more time or even a time after that to really get the ideas and really practice. But we hope this will help you with upcoming assignments. We hope it's going to help you better understand some of the content coming up in chapters 21, 22, and 23. And we hope you'll ask lots and lots of questions. If you're not really getting this, don't worry, you're not alone. You're definitely not alone. I can tell you that based on 20 plus years of teaching experience. You're not alone if this is not making a lot of sense. But we want to help you, so please ask a lot of questions and reach out for extra help. Okay, everyone, thanks for hanging in with me through chapter 18, and we will talk again soon in chapter 21.